more collision detection. So we now have all the tests to do. We have rect versus rect, point in rect, point in circle, point in random polygon. We have line intersection tests. How do we start putting it together? Well, something you're going to have to decide for your game is how you're going to be modeling your collision shapes around your objects. And for sake of physics, yes, physics, let's start talking about the space. The collision space is going to be our set of things that can collide. Now, in physics terminology, we would refer to them all as bodies, like a free body that can move around in space. In fact, if you've ever had a physics test or a physics class, you've likely remember one of your instructors referring to or saying the lines, let's start by drawing a free body diagram. And that's how they would start solving mechanics and dynamics problem. In our world, we are going to be creating the physics space. So for that sake, what I'm going to refer to not as entities, an entity may have a body, doesn't necessarily have to, but for the sake of collision, let's start calling them bodies. So a body is going to be a reference point in space that has a position. So we have our, where is it? We have our position in space. Depending on how fancy we want our physics simulation to be, we could add things like mass and momentum and angular momentum and friction for our surfaces and whatever else we would want to do. For this case, I'm just going to keep it as simple as I can to begin. So we have a reference point in space, an x, y, and z. This is our body. A body is going to have associated with it a type of shape. Now, if you are going to do something like a bullet hell, I'd recommend probably making everything uniform shape type. It'll make your life simpler, either all rectangles or all circles. But here's what I'm going to be doing for this shape. So a shape is now going to be part of this body. Now, since my circle is defined with x, y, and r, what I end up doing is the body's x and y position is its absolute position within the collision space. The circle's position is relative to the body. So my x and y is going to be an offset from my body's position. If there is no offset, then it's just going to look like that. But hey, it doesn't necessarily need to be that way. For instance, maybe I want to have this be the shape of my object. I've got a bounding box above it or below it or to the right of it or however I want to do it. But it's going to be an offset. Maybe it's 0, maybe it's some other number, however we want to define the shape of our things. There are arguments to have bodies that have multiple shapes. So if I want to describe some more abstract shape of something, perhaps I've got something remarkably crab-like that's going to have multiple shapes. Maybe I can have that. And I'll deal with the collision along that line. But for now, I'm just going to keep it simple. One shape, one body. And the body itself can also have properties like velocity, so my change in position over time. So give myself an arrow. I'm moving in this direction, and the length of my vector is how much I'm moving. What you want to do when you're designing your physics systems and your collision systems is to determine what other shapes we're dealing with. Can I move to that position? In fact, let's imagine we're dealing with multiple shape types. So can I move to this position? And what you'll do is you'll project that there. By project, I mean take the position of my thing, add its delta that it's going to be in, to take its velocity at its position, and then you'll have a new position. You'll take the offset from the shape and you'll add that together, and you'll have a shape now in collision space that you can then use to test against the other things in collision space. And if there's overlap, no, I can't move there. And that'll be great for most collision detection systems. The problem is when we have very large velocities, what happens then? If I'm moving this fast and I have this wall in front of me and I test down here, well, I can move there. So I move there. The problem is that I've now I've now blipped through, or I've clipped through my wall here. Depending on what you're doing with your game, as long as the speeds of the things in your game are sufficiently small relative to the sizes of the blocks that you're going to be dealing with, that might be enough. However, if there are very large velocities relative to the sizes of the things that we're dealing with, that is not going to be enough. What you'll end up wanting to do is simulating your space in slices of time. So if this vector represents how much I would move over one time index, what I can do is I can, in my collision space, for each of my bodies, actually make a second velocity that is, say, half that. So now I'm moving at half that velocity. And what I'll end up doing is I'll test everything twice. This also has the issue of if I had two bodies that were moving at cross paths to each other, I might intersect them. But if I'm moving at half this velocity, then it's far more likely you'll actually capture that interaction. It's meant to be parallel. So what you end up doing is for each, let's write this as a pseudo algorithm and pseudocode. For each body, test 1 over x, the velocities in the space. And then you're going to do this for from 0 to x. We'll just do it that many times. So however many things we're dividing, so in this case, if we're dividing by 2 or moving at half the velocity, we would then test everything twice. Generally speaking, it's usually more like 10. We'll cut it a tenth and we'll test it 10 times. If we are moving sufficiently large, I mean, this is something you get to calibrate. Most physics engines allow you to calibrate how much precision, how many tests you're going to do. Now, you might see a problem with this. If we're already dealing with a collision space where I have n number of bodies, and I'm already checking to make sure that I'm testing every body against every other body, I have an n squared problem. And you're now telling me I now need to multiply my n squared problem by a potentially very large constant, by how many iterations I want to do in this loop. That can become incredibly problematic. And this is indeed why physics simulations are oftentimes costly and problematic, because we have to cheat as much as we can. I can tell you right now, one of the, some tips and tricks for collision optimizations. First thing you want to do is start dealing with teams. Only things on only bodies on different teams should check for collision. So our algorithm here for each body, test velocity in the space versus bodies, and then skip if same team. You might also want to deal with layers. For instance, you might have an item layer. The item is the only person who ever needs to care about the items is, say, the player. I don't want my enemy bullets to clip against items. I don't even want the player to clip against the items. I just want to be able to test to see if the item is clipping the player. So maybe there's different layers. So this is another thing we can do. Or I have a foreground and a background. So only bodies on the same layer can clip. And that's another way we can optimize. But even more than that, we can break up the space. There's a couple of ways that we deal with in-game space for dealing with that. One is called, and this is really more applicable in 3D space, is a binary space partition, a BSP. Works better in triangle space when we've got like a world of triangles. What you end up doing is pick in a body space, find the centermost body, and set that as your root of the tree. And then divide the world in half based on that. If we're dealing with 3D space, we would use the plane of what we're dealing with to bisect the world. And we'd then, on each half, we'd find the centermost point of that half and split the world, the remaining half, down by that half, and so on and so forth until every polygon exists within the binary tree, which gives us log base optimizations. What works better in a 2D space is something called a quad tree. Similar kind of way of breaking up the world, but the way the quad tree is going to work is you have the world in some sort of rectangle. You literally find something at the center of the rectangle, and that becomes the root of your tree. And then you end up bisecting that further. Or actually not even bisecting, you cut it into a quarter of the space. I'm being kind of sloppy here, but watch. It's going to work, I promise. So I've got all of these selected, and now I'm just going to scale them to about EA. And then when I'm adding entities into the world, I pick which one I'm going to add, which quad I'm going to be. If this quad already has something in it, then I bisect it even further. So what I do is I take this, and then I bisect that down, or quad-sect it. And then I'm adding another entity, and I'm going to add it into this world. Well, which quad are you going to go into? Okay, this quad's already got some stuff, so now I'm going to reinsert all of the things down into that. I'm going to drill down even further. We divide it even more, and then so on and so forth. So this becomes an unbalanced tree to search through. But what's cool about this is that you don't actually have to have a lot of information stored if there's sections of your map that don't have a lot of activity. So that's how you would end up with a quad tree. I don't think I explained that well, but we'll discuss it further in Discord. That's a quad tree. Now let's talk about the one that is probably most used in 2D, which is called a spatial hash map, or spatial hash. That's a spatial hash map. Spatial hash maps divide the world up, similar to the quad tree, but into uniform cells. So let's make a new thing. Spatial hash, and that's with a T, as I learned in the previous slide. And what that's going to look like is insert. Let's go with a table. We have uniform cells that make up the game world. And whenever we add something to the game world, we are going to add a reference to it. So this is, consider this a list of, well, lists of like, lists of pointers to entities, or bodies in this case. We add, as things move through our world, we add ourselves to each of the buckets that we happen to be colliding against. If you make sufficiently sized buckets relative to the size of your entities, then maybe I'm only in a few buckets. Might even want to make it so that there's a possibility I'm only ever in 1 or 2 buckets. And you can even just approximate that by rectangle, not by circle or something. So you just do like a raw rectangle. What buckets or cells am I overlapping whenever I move to a new position? Add me to those. And then usually before you move, you keep track of which buckets you were in previously, and you remove yourself from buckets. So remove yourself from all the buckets, move your new position, and then add yourself to the buckets you're clipping. And that way, when I'm doing a collision test, at this part of it, test the buckets that I happen to be clipping in versus the bodies in which case I massively reduce the number of collisions that I have to work with based on that. Now, mathematically, I forget what the actual O is. It still can potentially be a very large O if I happen to have a situation where I've got a massive number of things all in the same place. And then managing your buckets is going to take up space. So this does take up a lot of memory, potentially. What I generally do is I've designed my GFC list type to dynamically expand, but it will not contract. And it's probably a good point to make each bucket a list, a GFC list. The idea being that if I've got a game with sufficient complexity, sufficient number of things colliding, it's probably going to be around the same locations. So there's points of heat where a lot of activity happens. And what I would do is, as things are active and then go away, like a whole lot of bullets are fired and then are cleaned up. If it was active there once, it's probably going to be active there again. And then once everything is inactive, it's probably because I've completed the level and the whole thing's going to get cleaned up anyway. So I don't bother shrinking any of my buckets. And generally there's going to be an upper bound for how many entities can possibly exist at the same time anyway. So I don't have to worry about this becoming a runaway memory leak in practice. So organize all bodies into the buckets that are clipped. And that's what we'd be dealing with. And then only clip against bodies in same buckets. So instead of checking the entire world of bodies, I'm just dealing with the bodies that happen to be in these 6 buckets. And then and maybe I'm the only entity in there, in which case it's instantly, you don't have to even worry about any of my collision tests. That's how you can deal with optimization for that. All right, so this has gone into now advanced topics as well. So I'm going to stop this video here and